This is part 3 of the series Congruent Triangles, in which we're exploring relationships within and among triangles. And we're going to start this session with the exterior angle theorem. And remember that an exterior angle is an angle outside the triangle whose sides are a side of the triangle, an extension of an adjacent side, and that angle makes a linear pair with its interior angle adjacent counterpart. So the theorem states that the exterior angle is the sum of the measures of the two non-adjacent interior angles. These are also called remote interior angles. And so the measure of angle 1, this exterior angle, equals the measure of angle 2 plus the measure of angle 3. So let's go ahead and prove this and see where these relationships come from. So to prove this theorem, we're given this triangle, and we haven't even labeled it. We don't really need labels on the outside, and an exterior angle here. So let's just jump right. As we've talked about before, the best way to proceed with proofs is to have some idea of a plan for your proof. What is it that you're going to try to accomplish? We know we're trying to get to the measure of angle 1 equals the measure of angle 2 plus the measure of angle 3. We can see that these three angles are going to sum to 180 degrees. We can see that these two angles are a linear pair, so therefore they're supplementary, so they sum to 180 degrees. And we should be able to do some sort of a substitution in here to replace this with these and hopefully get a relationship between angle 1 and 3 and 2. So there's a really rough sketch of our plan for our proof. So let's go ahead and write the first thing what we said here. We said that this plus this plus this equals 180 degrees. So we know that the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 equals 180 degrees. That is the triangle sum theorem. Again, this is the Greek letter sigma, which stands for sum. Alright, we also know that these two are a linear pair. So angle 1 and, that's an N, angle 4 are a linear pair. That's definition of a linear pair. We know that angle 1 is supplementary to angle 4. Remember what the reason is? That's the linear pair postulate. Linear pair postulate says linear pairs are supplementary. Well, because linear pairs are supplementary, we know that the measure of angle 1 plus the measure of angle 4 equals 180. So that's the definition of supplementary angles. Okay? Now, we use the fact that this plus this plus this equals 180, and this plus this equals 180. Hopefully you'll see a pattern in here. If A equals B and B equals C, then A equals C. That's the transitive property of equality. So we can say, might need a little more room over here, measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 equals this, measure of angle 1 plus the measure of angle 4. And that is the transitive property of equality. Now we can see here that we have an angle 4 and an angle 4 on both sides. So we're going to subtract those out, and what we have is the measure of angle 2 plus the measure of angle 3 equals the measure of angle 1. That is subtraction, property of equality. And there we have our proof. We said the measure of angle 1 equals the measure of angle 2 plus the measure of angle 3. If you wanted to be puristic about it, we could swap sides with these two using the symmetric property of equality, but it's really not necessary. You can see the nature of our proof here. We've shown that the exterior angle equals the sum of the two non-adjacent interior angles. And so let's do some examples. With any of these examples that we do, it's always a good idea to see if you can go ahead and work the problem out yourself and then go ahead and start the video back up just to check your answers. But it's up to you how you want to handle it. So here we have the exterior angle theorem again, and we know that this plus this is going to equal the exterior angle. So we say 70 plus x equals 2x minus 5. So I like working with positive numbers, so I'm going to move this x over here. So I have 70 equals x minus 5. We just subtracted x from both sides. Add the 5. 75 equals x. So we know that x is 75, and so the measure of this angle is going to be 2 times 75 minus 5, which is 150 minus 5, that's an equal sign, which is 145. Let's try another example. So here we have another example of the exterior angle theorem, and it's just in a different orientation. So here's your exterior angle, here's your two non-adjacent interior angles. So this angle, 5x minus 10, is equal to the sum of the two non-adjacent interior angles, 3x plus 40. So again, I want my x is positive, so I'm going to take the 3 and move it over here. So we have 2x minus 10 equals 40. Add the 10, 2x equals 50. X equals 25. Now if we want to find the measures of these angles, we know that this angle is 3 times 25, which is 75 degrees. And this one, we have, I don't have enough room over here, so we'll just do this over here. So 5 times 25 minus 10 equals 5 times 25 is 125 minus 10, which is 115. So that means this exterior angle is 115. And that makes this angle 65 degrees because these are a linear pair. So let's just cross-check ourselves. Let's add these three angles up. 65 plus 40 plus this angle is 75 does in fact equal 180. So we can conclude that our answers are correct. So let's go ahead and move on to the next section. In this section, we're going to talk about congruent polygons, and we're going to extend that discussion to specifics of congruent triangles. Now, before in the past sections we talked about what it meant for two polygons to be congruent. We said that two polygons are congruent if and only if there's a rigid motion or composition of rigid motions that maps one polygon to the other. Now, there is also another definition. Two polygons are congruent if all of their corresponding parts are congruent. So here we have two quadrilaterals, and we can see that angle A and angle E are congruent because this one has 4 arcs, this one has 4 arcs. Angle D is congruent to angle F because they have matching arcs. Same thing with AD, FE, and so on. So you can see that all the corresponding parts of polygon ABCD are congruent to the parts of EFGH. Now, to state that these two polygons are congruent, we would form what's known as a congruent statement. And congruent statements are going to be a very vital part of solving problems, as we're going to see in the very near future here. So to form a congruent statement for this, let's start with A. So we'd say A, B, C, D. I just went in an arbitrary motion clockwise here. Now we need the vertex that's corresponding to A. So this is congruent to. The vertex that corresponds to A is the one that has the 4 arcs. So that's E. The one that corresponds to B is H. The one that corresponds to C is G. And finally F. Now this order is critical because this tells us that this vertex corresponds to this vertex to this one to this, and this one to this. It also gives us a relationship for the sides. You'll notice that AB here has 4 hash marks, and EH has 4 hash marks. GF is in the same position as CD. CD has 2, GF has 2, and so on. So these congruent statements are critical in being able to determine what part corresponds to what part in these congruent polygons. So just as a quick exercise for you, see if you can complete the congruent statement I'm about to make. I'm going to say that triangle BAC is congruent to which triangle. So go ahead and stop the video, see if you can fill that in, and then restart. So what you should have gotten was B corresponds to E, so this would be triangle E. A corresponds to D, notice the hash marks. And C corresponds to F. So triangle BAC is congruent to EDF. If we had said triangle BAC is congruent to FDE, we would have been incorrect because those vertices do not match these vertices. So let's go ahead and try an example. So here we have DEFG is congruent to PQRS. We're to find the values of X and Y. So I don't want to solve for this one first because it has X and Y in it. So let's solve for this one. So we need a side that corresponds to SP in this figure. So SP is this. That corresponds to DG. DG is 12. So we know that 12 equals this side. 2x minus 4. Let's add 4. 16 equals 2x. 8 equals x. Now let's solve this guy. Well, vertex P in this figure corresponds to vertex D, which is 68. So we know that 68 equals 6y plus x. 68 equals 6y plus 8. 60 equals 6y. Y equals 10.